Okay, in the first part of this discussion of the P212121 lattice, we explicitly considered a small number of tensor elements inside the molecular frame and mapped those onto a small number of tensor elements in the crystal frame. What we're going to do in this one is show how we can use symmetry operations and symmetry matrices, introduce symmetry matrices in order to generalize this architecture. So if there is any simplification due to symmetry, how do we take advantage of that while still maintaining this mathematical framework all based on manipulating all 27 elements through these 27 by 27 rotation matrices describing the Kronecker products? We actually only had to evaluate a small number of elements here and a small number of elements here, bearing in mind symmetry, but before we did that, we had a full set of 27 here. And so we introduced symmetry operations, or symmetry matrices. So these symmetry matrices, for this one here given by S, allows us to populate the full set of 27 elements in beta prime from the small subset of unique non-zero elements in beta. So we know, for example, in this case, there's only 2 non-zero unique elements in beta within the limits of the assumptions, but we have 27 elements that we can plug into this equation if we want to populate and evaluate what the full set of 27 elements in the crystal frame. So how do we generate the full set of 27 elements from the set of 2? Well, we're going to multiply it by a 27 by 2 matrix. So we can basically, and that's what this symmetry matrix is here. It's a 27 by 2 symmetry matrix. And this one is actually pretty straightforward and trivial to evaluate in the present case because it's going to be almost all zeros with 2 ones, and those 2 ones are going to correspond to beta xxz and beta zxx and beta zzz. So if we want to know where to put them, then it's really a case of so before we figure out how to populate, so we know we have those 2 tensor elements to populate. So before we go about the actual population of that symmetry matrix, it's worth going back a step and just reminding ourselves the basics of ternary counting, because we're going to have a whole bunch of tensor elements we're going to have to identify based on the indices and where we put them in a matrix. And in the decimal position of any ijk tensor element, if I want to vectorize it, it's going to be given by this ternary counting algorithm. So just, you remember binary counting. Well, we have x, y, and z possibilities for each individual index, and we have 3 of them. So the ternary counting system goes as shown here to the right of this table, and this basically counts all the way up from 0 to 26, where 26 would be the last element. So, for example, if we want to consider what beta zxx is in a vectorized form, what position that occupies in the vectorized form of beta, that entry is going to correspond to 9 times 2 for the z, plus 3 times 0 for the x, plus 0 for the x. So that will correspond to position 18 in beta in the vectorized form. And beta zzz should end up being 26. Let's just convince ourselves of that. There will be 9 times 2 plus 3 times 2 plus 2. And sure enough, you add those up, and that corresponds to position 26. So we have 2 non-zero terms, positions 18 and 26 in beta. So if we go back to this symmetry matrix S, what are we going to do? We're going to say that if I'm defining, I keep wanting to think it's xxz, z, xx, and beta z, z as my set of unique non-zero elements, and I'm going to multiply that by S to make the full set of 27 elements, then I know that S, it'll be, let's see, this is the 0 position in beta. That will correspond to 18,0 is going to equal 1. So that will populate the ZXX position in the full set of 27 with the 0 entry in this reduced number of unique non-zero elements. And then S26, 0 is also equal to 1, and all other entries are 0. So it's a sparse matrix with 2 non-zero entries, and that can generate the full set of 27 elements in beta. We can do the exact same thing on the backside, because what we have is a set of 27 elements in chi, but we actually only care about the 6 unique non-zero ones that are allowed in a crystal of P212121 symmetry. So how do we approach that? Well, the exact same thing. We can populate, if this is the unique set of 6 elements, and this is the full set of 27, we can make Q just by exact analogy with how we made S, finding the non-zero elements and then populating them one-to-one over into chi to generate a smaller subset. And then we can take the transpose of that, and now what we have here is a 2-element vector on the right and a 6-element vector on the left. I mean, don't do that to me. And then this 27 by 27 set of rotation matrices inside. And because this is known and these two symmetry matrices are known, we can fold them into the rotation ensemble average if we want to reduce the total number of elements we have to consider in terms of the evaluation of the orientational averages. When we apply these symmetry operations, it's just going to pull a few rotation matrices out, rotation matrix combinations out, and those will be the ones that connect the unique elements in the molecular frame to the unique elements in the laboratory frame. So that's sort of a nice framework for generalizing to arbitrary symmetry while still taking advantage of the fact that you have symmetry to reduce the complexity of the analysis.